Alright everybody, final section, we're going to talk about measuring earthquakes. So the first way to measure earthquakes is called the Modified Mercalli Intensity Scale. And what is this? We're looking at the maximum intensity of shaking. Now this particular scale is going to vary from place to place because there's more shaking in some spots than in others. In other words, the further away you are from the epicenter, the lower of a reading you get on the scale because there's going to be less shaking there. Now this one in particular is based on descriptions of whatever people feel and see and whatever damage that they notice. It's all descriptive. It's on a scale from 1 to 12, and it tends to be a scale that's a little bit more meaningful to the public at large. So this is the actual scale here. Everything from 1, nobody could feel it, all the way up to 12, everybody feels it. And you can tell, maybe it's a little bit hard to see, that these are descriptions of what a person might see if they experienced an earthquake with shaking at, say, a level 6, right? This would be felt by everybody in the area. Many people are frightened and run outdoors. They might walk unsteadily. Windows or dishes or glassware is broken. It's completely descriptive, which makes it very, very useful for being able to communicate the intensity of an earthquake to somebody who is not a scientist. The other scale that we'll use is called the Richter magnitude scale, and this is measuring the amount of energy that is released in an earthquake. So the magnitude of the earthquake depends on the surface area of the fault that caused the earthquake. Bigger fault means a bigger earthquake. And these seismographs are going to tell us what the amplitude is of the waves, how big the waves are of the earthquake, and based on the amplitudes and a couple of other pieces of information, you can put together the magnitude. Now, this one is an exponential scale, or a logarithmic scale. And what does that mean? So let's say we go from a magnitude 7 earthquake to a magnitude 8 earthquake. Well, this is going to be 10 times more shaking for a total of 32 times more energy. Now let's go 2 steps here, right? We go from a magnitude 7 to magnitude 8 all the way up to a magnitude 9. 2 steps here. It's going to be 100 times more movement, or about 1,000 times more energy. It's an exponential scale for this one. There is also this inverse relationship between the magnitude of an earthquake and how frequent that level of earthquake tends to be. In other words, as the size of the earthquake goes up, the frequency of the earthquake goes way, way down, to the point where earthquakes at the very top end of the scale, 9 or more, tend to be extremely rare events. Now, there's also included on this graph for reference the atomic bomb dropped on Hiroshima. Be about a magnitude 6.2 earthquake in terms of the energy equivalent, not shaking, as well as the world's largest nuclear test done in the USSR would have been about equal to a magnitude 8 earthquake, just for reference here. All right, now the people have asked for math, and I'm going to give them math. What we're going to do here is we're going to look at this graph, this seismograph, and we're going to figure out, finally, the magnitude of this earthquake. So our first step, we need to identify either the distance away from the earthquake or the S minus P interval, the time difference between the S and the P waves. So we can look up here. All right, this is about where the P wave starts. We have our scale, and we read, oh, that's maybe about 25 seconds here. So we're going to plot. It's about 25 seconds on this graph. Now, next step is the amplitude. We can come up here and we look, okay, well, this is the wave that reaches furthest away from the baseline, from the zero. It's going to be right here, and it measures in at about 23 millimeters. So go ahead, plot 23 millimeters. Now, finding the magnitude, we draw a line in between these two, and the magnitude of this earthquake is going to be where this line that we just drew crosses this in the middle. It's going to be about a magnitude 5. I want to talk a little too about the largest recorded earthquakes. So here we have them plotted on the map. The pattern should look familiar. This is everything which is rimming the Pacific Ocean here. Where are they? All around the Pacific. These are also going to be the site of subduction. These are going to be at convergent plate boundaries. Now, what about the largest that an earthquake could ever be? What is the maximum possible magnitude for an earthquake? And there's 2 ways to sort of answer this, right? You have no hard limit on how large an earthquake could be on the one hand, but really there's not a fault big enough on Earth to produce a magnitude 10. Earth has a lot of faults. Some of them are very big, but none of them are big enough to produce a magnitude 10 earthquake. So that is the practical limit for how large an earthquake could be. There's also this sort of theoretical limit to it. If you had a magnitude 12 earthquake, the size of the fault needed for that would literally split the entire Earth in half. So even in the wildest scenarios imaginable, a 12 is about as large as an earthquake could ever be. Okay, so let's put it all together. What are the big ideas when it comes to earthquakes? Well, first, what are the basics? What is an earthquake? How does it happen? And where do earthquakes normally occur, both in the United States and in Arizona specifically? What are the types of faults involved here? What are the differences between primary and secondary hazards? What are the different types of waves involved? And how could we use those waves, how could anybody use those waves, to study something about the Earth's interior? That is all I have. Thank you.